All right, welcome everybody to today's set theory seminar. We have Andreas Lietz from the University of Münster. He's currently working on his PhD thesis under the supervision of Ralf Schindler, and he's going to talk about a part of what he's doing for his PhD. And it is about forcing the non-stationary ideal on omega-1 to be omega-1 dense from large cardinals, part 1. And I thought there was something with A Journey Guided by the Stars. It was such a poetic title, so you changed
It's
it.
here. It's a little
Oh, yeah,
small, but
okay,
it's
all
there.
right, just small print. Okay, all right, yeah, go ahead, Andreas, looking forward to it.
Yeah, thank you very much for the nice introduction. Yeah, I'm very happy to be here, and thank you for the opportunity to let me speak here, and also next week to give the second part of this talk. So exactly, I will try to sketch how you can force the statement the non-stationary ideal is omega-1 dense from large cardinals. And well, I will try to explain. Hopefully, it becomes clear what this small subtitle here means as we go along. It's sort of the stars are sort of our navigation system, which tells us what to do. All right, so let's begin with some history of the problem, what it's about. So clearly, omega-1 is not measurable, at least in the context of ZFC, where we have the axiom of choice. But it can be generically measurable, which means that it sort of is measurable, but just the witness for that is in a generic extension. So, I mean, in a generic extension, there's a definable elementary embedding from V into a transitive inner model, which has critical point the omega-1 of V. And so this idea, it leads to the notion of a precipitous ideal, which I will introduce shortly. So that omega-1 is generically measurable. It's not equivalent to the existence of a precipitous ideal, but precipitous ideal guarantees that this is true. So what is a short convention? So just so that I can spare a few words. All the ideas of this talk will be uniform and normal and omega-1. So whenever I forget to say one of these things, it's always uniform normal ideas on omega-1. And we say an ideal is precipitous if, so first of all, to any ideal on omega-1, you can associate a forcing, where you force with the positive sets. And what this does, it turns the ideal into a prime ideal, at least for V. So then it measures all subsets of omega-1 in V. And this prime ideal, then this generic prime ideal has a dual ultra filter, or V ultra filter, I should say. And then you can take the ultra power of V by this generic V ultra filter. And we say that the ideal is precipitous if this ultra power is always well-founded, no matter what generic filter you take. So the ultra filter will depend on the generic you take, and so no matter what generic you take, the ultra power is always well-founded. And this, of course, then gives you an elementary embedding from V into this ultra power right here. So omega-1, and it will have critical point the omega-1 of V. So omega-1 of V is generically measurable. So some history on precipitous ideals. So Mitchell showed in the mid-70s that precipitous ideal on omega-1 can be forced from the measurable cardinal kappa. So what you do is you just collapse kappa to omega-1, and then sort of a measure that witnessed in V that kappa is a measurable cardinal. It will generate an ideal in this generic extension, and you can show that this ideal is precipitous in this extension. And whenever you can make some ideal have a certain property, there's like a canonical normal ideal on omega-1, which is a non-stationary ideal. And then you can ask whether you can have the non-stationary ideal have this property. So then Markidor went on and he further developed this method of Mitchell, and showed that the non-stationary ideal on omega-1 can be precipitous, and this can be forced from a measurable cardinal. So what you do, you first do what Mitchell did, and then afterwards you sort of reshape the non-stationary, this ideal that you get, the precipitous one, into the non-stationary ideal. And then you have, of course, to check that it stays precipitous, and you can make this work. And then there's a natural strengthening of precipitousness, which is called saturatedness. So you say an ideal I on omega-1 is saturated if the associated forcing here is omega-2 CC. So you have no long anti-chains of I positive sets. And all saturated ideals are precipitous. So it's a nice exercise, I think, to show this if you haven't seen this before. And then the history on saturated ideals as follows. So CUNY was the first to force a saturated ideal, and he did so from a huge cardinal. And in fact, he invented a huge cardinal exactly for this purpose, or discovered them, depending on what your perspective on these issues may be. But this was not the non-stationary ideal. So again, you can ask, can you turn non-stationary ideal to be saturated? And indeed, you can. So this was first done in the work of Steele and Van Weesep. And they showed that you can force that the non-stationary ideal is saturated over a canonical model of AD plus ACR. And this model would, of course, be a model of ZFC. So how does determinacy come into play here? Maybe it looks a little surprising. The idea is that under the axiom of determinacy, omega-1 is in fact measurable. And the axiom of determinacy is quite a strong principle, and it implies a lot of structure, at least for canonical models of the axiom of determinacy. And so you can ask, can you force over these canonical models of AD? Can you make choice true, get a generic extension which is a model of choice, and preserve some of this measurability? And of course, you cannot preserve full measurability, but you can get close to it by for example, getting the non-stationary ideal to be saturated. So also this assumption was shortly after reduced to just AD by Wooden. And then Foreman, Magidor, Shelar, they showed that you can force this statement from large cardinals, in fact. And they did it from a super compact cardinal first, and you can even do it by semi-proper forcing. And well, the way they did it is they forced the forcing axiom Martin's maximum, and showed that the Martin's maximum implies that the non-stationary ideal is saturated. And then later on, this was so the large cardinal assumption was reduced a lot by Shelar, so you can actually force that the non-stationary ideal is saturated just from one Wooden cardinal alone. Okay, so now let's get to further strengthening of saturatedness, which is omega-1 density. So we say that an ideal I on omega-1 is omega-1 dense if the associated forcing has a dense subset of size omega-1. So clearly, if that's true, then the ideal I is saturated, because every anti-chain, you can strengthen each element to be in this dense set, and they must strengthen to different elements because it's an anti-chain, and since this dense set only has size omega-1, there can be no large anti-chain. And well, it's quite a strong strengthening of saturatedness because so if the ideal I on omega-1 is omega-1 dense, then the structure of this Boolean algebra right here is completely determined. So it can only be one thing, can only be the complete Boolean algebra sort of extension of the collapse forcing. So while when you're just looking at saturated ideals, the associated Boolean algebra, you can have different structures. Anyway, so in this sense, it's sort of, you could say, a maximal strengthening of saturatedness because it tells you exactly how this complete Boolean algebra here looks. Okay, so can you have this? is this possible? So Wooden has proven a lot of theorems on how you can generate omega-1 dense ideals on omega-1. So he first showed that an omega-1 dense ideal on omega-1 can be forced over a canonical model of ADR plus theta's regular. So he proved this in 1978, which was quite a while actually before the assumption was actually known to be consistent from large cardinals. Like this only happened in the mid-80s, I believe. So naturally, afterwards, he produced an omega-1 dense ideal from a large cardinal assumption. So you can force an omega-1 dense ideal on omega-1 from an almost huge cardinal. And now, once again, you ask the question whether you can have the non-stationary ideal on omega-1 be omega-1 dense. And indeed, it's possible. And he did so by forcing over canonical models of the axiom of determinacy. For example, you can do it over L of R, assuming that the axiom of determinacy holds in L of R. But well, this is, in some sense, this is sort of that you can only do it over canonical models of AD that are well understood. You can understand it sort of as an anti-large cardinal hypothesis. So Wooden's method of doing this doesn't answer the question whether, say, all natural large cardinals are compatible with the statement, the non-stationary ideal is omega-1 dense. Well, for example, it's not clear from this method whether like a super compact cardinal can exist and the non-stationary ideal on omega-1 can be omega-1 dense, or whether like strong combinatorial principles like the strong reflection principle can hold while the non-stationary ideal is omega-1 dense. And well, I mean, he showed that from large cardinals you can force some ideal to be omega-1 dense, but well, the non-stationary ideal in this case, it behaves a little bit differently than just some other ideal. So in the sense that this statement here, it actually implies that the continuum is the same as 2 to the omega-1. So CH fails. So this is the result of Schiller. While the model that Wooden gets by forcing with an almost huge cardinal, it's a model of CH. So it's possible that some ideal is omega-1 dense and CH holds, but if the non-stationary ideal is omega-1 dense, then CH must fail. Okay, so then Wooden asks this question, whether you can force the statement assuming just large cardinals. So the question is, some large cardinal, is there a semi-proper partial order P so that in the extension by P, the non-stationary ideal is omega-1 dense? So, and I should remark that, so this question, it was even open without the restriction to semi-proper partial orders. So Wooden decided to make this question a little bit harder by putting in this extra restriction. Anyway, so the goal of my talks here is to sketch a positive solution to this question. So what we'll show or sketch is that assume that there is an inaccessible limit of supercompact cardinals. So we're free to use any large cardinal solution that we want. And this is one that works. Then there is a semi-proper partial order P, which forces that the non-stationary ideal on omega-1 is omega-1 dense. Okay, so what's the strategy? So it all begins with the result of Davita Sparrow and Schindler that Martin's maximum plus implies star. So let me remind you what the axiom star means. So it's the conjunction of saying that the axiom of determinacy holds in L of R, and that you can find a filter for the partial order Pmax, which is generic over L of R, and such that in this generic extension, all subsets of omega-1 are included. All right, so now the way he showed that you can force a non-stationary ideal to be omega-1 dense over L of R, assuming the axiom of determinacy there, is that he devised this Pmax variant that he called Qmax. I assume because Q is the next letter in the alphabet after P. If you force this over L of R, then you will get a model of ZFZ plus a non-stationary ideal on omega-1 is omega-1 dense. So now you can, in this definition star, you can replace Pmax by Qmax. And this gives you the axiom you call Qmax star. And well, whether or not the non-stationary ideal on omega-1 is omega-1 dense, it depends only on the power set of omega-1. So if Qmax star holds true, as witnessed by such a filter G, then this extension of L of R and V have the same power set of omega-1. And by this theorem of Wooden here, this guy believes that the non-stationary ideal on omega-1 is omega-1 dense. So in V also, the non-stationary ideal on omega-1 must be omega-1 dense. So Qmax star implies the statement that we're looking for. So exactly, this is what I just said. So maybe now we can have the same story between MM++ and star, but for Qmax star instead of the usual star. So essentially, we try to solve this equation for X. We're looking for some forcing axiom that behaves to Qmax star in the same way that MM++ behaves to star. Okay, so how can we find it? So I will try to motivate how you can come up with this forcing axiom. So what we do is we reverse engineer sort of how you could force such a thing. So we just assume that this forcing axiom exists and we use some intuition. We know how usually strong forcing axioms like PFA are forced. It always looks sort of similar. So you assume some large cardinals exist, and then there should be a countable support style iteration of length this large cardinal kappa. So maybe this is super compact or something similar. And so assume it forces this axiom. And then let's try to reverse engineer this forcing iteration. So in the generic extension by P, then this forcing axiom should hold. So this forcing axiom should apply that the non-stationary ideal on omega-1 is omega-1 dense, as it should imply Qmax star. And this is in fact equivalent to there being a dense embedding from the collapse forcing of omega-1 to countable into the associated forcing with the non-stationary ideal, simply because this collapse forcing is the only forcing of size omega-1 which collapses omega-1. And if you force with this guy, you always collapse omega-1. Okay. So, but then actually, so these iterations, they iterate forcings of size less than kappa. And then as a countable support star, the sole iteration must be kappa CC. And this means that sort of some representation of this dense embedding should exist, should appear already at some earlier stage. So by representation, I mean is that you associate to each condition in the collapse forcing one stationary set, which has the same equivalence class in this Boolean algebra as what this embedding eta says. Okay. So here we have kappa, And here we have alpha, so this eta 0 already should appear in VG alpha. And then, so this eta 0, it cannot be anything. Like, I mean, it has to have some properties. And maybe it has some properties that already must hold in VG alpha. And yeah, this is true. So you sort of try to look for the correct pi1 fragment of what this eta 0 should satisfy in VG. And this should already be true in VG alpha. And then maybe forcing such an eta 0 with this weaker pi1 fragment property is easier than solving the whole problem. So maybe we can force this easily. And then what we should actually do is we should first force this, and then afterwards do an iteration which preserves this property. And well, and what should also happen is that it should turn this eta 0 into sort of a dense embedding along the way. So this is sort of how the iteration should look like. So how do you come up with this correct, this pi1 fragment, this correct property that eta 0 sort of should have? So in the whole extension, the non-stationary deal is omega 1 dense. So suppose we force with it, and this then generates an elementary embedding from VG into the alter power. And in fact, this generic H here, it generates a generic for the collapse forcing along the dense embedding eta that we had. And in fact, this small h must be in the alter power. And there's a canonical function which represents the small h in the alter power. And you get to it like this. So you define a function e by mapping a countable ordinal alpha to all conditions p in the collapse of alpha, for which alpha is in eta 0 of p. So remember, eta 0 was this representation of the dense embedding eta. So eta 0 of p is really a subset of omega 1. And then a quick calculation shows that this function e always represents this little h in the alpha power after you force with the non-station idea. Okay, so and then this was already done by Woodin. So he isolated this principle. So you sort of try to isolate nice pi1 properties that this function e has. So and then you can come up with this definition. So we say that f witnesses this diamond principle. So in fact, I don't really know how to pronounce this principle. I should ask you about this, but we'll just call it a diamond principle. So f should guess filters for the collapse forcing, by which I mean that f of alpha should be a filter in the collapse of alpha to become countable. So the function e here, it almost has this property. So almost always, for almost all alpha, e of alpha must be a filter, because it always represents a filter in the alter power. So almost always e of alpha must be a filter. So, but for the sense of this definition, we say that it's true everywhere. And then another property that e must have. So suppose you give me a sequence of omega 1 many dense subsets of the collapse forcing, and you also give me a condition in the collapse forcing. Then I will be able to find countably many alphas for which both this condition is in the filter given by f at alpha, and also f of alpha hits many of these dense sets. So not all of them, but at least all which are indexed by an ordinal less than alpha. So we can say that C that E has this property because, okay, so you give me the sequence, and then we can look at J of the sequence. So how does this look like? It's a sequence of lengths j of omega 1. And for indices less than the omega 1 of G, well, let's just write omega 1 for omega 1 of G. The di tilde is just a stretch of di. So di tilde intersected with the collapse forcing is exactly di, right? And well, we have that j of E at omega 1 is exactly H, right? And H is generic over Vg, and all these di's, they are in Vg. So this thing here hits di, and so it hits di tilde. Okay, and okay, I didn't talk about this extra condition that you give me, but I could choose the capital H, so such that it contains eta of P of this condition, and then it would also be true that P is in here. Okay, so in the end, this tells you that E has a second property. All right, so this definition here, it captures exactly the property sort of eta 0 that we want to keep. So this function E and eta 0, they are in fact like interchangeable. They code each other in some way. And yeah, also from such a witness F right here, you can get an embedding eta F like this, which in the case of the E before would be the eta 0 essentially. So so here think of this analogy of eta 0. So you map P to the set SFP, which contains all ordinals alpha, for which the condition P is in the filter f of alpha. Okay, so to get back to this image, so we have some large cardinal kappa, and we iterate up to kappa, and at some earlier stage alpha, we get this witness of the Steinmann principle. And what we should try to do for the rest of the iteration is preserve this property of F. So F should stay such a witness along the iteration. And well, simultaneously, what also must happen is that along this iteration, we turn this map eta F into a dense embedding. And well, turning this eta F into a dense embedding, you can only do by so most likely it would not be true at stage alpha already, because I mean then it would be already done, at least for the property that we care about. And if it's not true at stage alpha, then the only way that this can happen is that we kill stationary sets along the way, along the iteration to kappa. So by the way, I promised you a semi-proper forcing in the end, and I should mention that this iteration from this point onwards, I mean, it kills stationary sets, so it's not an iteration of semi-proper forcings, but only in the very end, actually, we can see that we can arrange the whole iteration, the whole forcing to be semi-proper. But this only happens really in the end. So for the moment, we should care about how we can iterate and kill stationary sets along the way. And in the best case, we can also preserve that F has the Steinmann property. But we will forget about the Steinmann property for a moment and more focus on iterating killing stationary sets. By the way, now we can actually formulate the correct analog of ML++ in our case now. So we call QM for Q maximum, and it just states that there's F a witness of this diamond principle, and the forcing axiom for the class of all forcing which preserve F holds. So this just means that in VP we have still that F witnesses this diamond principle. Okay, and the forcing axiom, so maybe I should explain this also. So this just means that if you give me a sequence of omega-1 many dense subsets of such a P from this class, then I can find some filter which meets all these dense sets that you gave me. So just typical forcing axiom. Okay, so yeah, here's also the theorem. So yes, so this forcing axiom, it implies Qmax star, so it's a correct analog for Qmax star in the case of Qmax star of MM++, and it's also consistent from large cardinals. So if there is a supercompact limit of supercompact cardinals, then there's a semi-proper forcing which forces QM. So, and from my perspective, this proving this theorem is really what's behind this question of Wooden, as far as I can tell. So it seems like doing the one leads to doing the other. Anyway, so okay, it's maybe you should, yes.
Just a quick question. So it's not an iteration of stationary set preserving forcing slope, right? So
no.
It's a situation that during the iteration you can kill stationary sets that were introduced during the iteration, but you preserve all the stationary sets from the ground model. Is that the?
Yes, exactly. This is exactly what happens in the end. Yeah. Okay, we will look into this along the way. Okay, so first of all, so it's quite difficult to show that QM implies Qmax star, but it's way easier to show that QM implies that the non-stationary ideal in omega-1 is omega-1 dense. And I will give you a quick sketch. So suppose F is witness of QM, and we want to show that the embedding eta F is associated to F, that this is a dense embedding. Okay, if not, then there is a stationary set such that no set of the form SFP is almost contained in S modulo the non-stationary ideal. So this just means that for all P, SFP minus S is still stationary. And then you look at the forcing which kills the canonical forcing which kills S. So you shoot a club through the complement of S, and okay, I'll leave the details to you, but this forcing indeed preserves F, but you cannot have a forcing axiom which applies to a forcing which kills a stationary set. Yeah, because you must have that the H omega 2 of V is the sigma 1 elementary substructure of the H omega 2 of the forcing extension. And well, if the stationarity, if S is non-stationary in the forcing extension, it's just a sigma 1 statement, it must be true in V. So you get a contradiction. Okay, so modulo the details here. This shows that QM implies a non-stationary ideal, and omega-1 is omega-1 dense. All right, so let's get to iterating forcings which kill stationary sets that I promised you. So for the moment, let's keep things simple. We will forget about F and like witness of this diamond property. And so let's just look at iteration of length omega of forcings which preserve omega-1. And I say we hope to show that P preserves omega-1. I say hope because it's not true. You cannot just prove this generally. There are different counterexamples to this. There are different iterations of length omega-1, which of length omega, which have this property, but destroy omega-1. But it's instructive to try to prove it anyway, and then inevitably something must break, and then we will look how to fix that. So you get into the typical setup of iteration theorem, which tries to emulate sort of the mother of all iteration theorems, which is Scheler's iteration theorem for proper forcings. So the setup is always, you have some condition P in the forcing, and you have some countable elementary substructure of some h theta, and theta should be some large regular cardinal. And well, the forcing should be in X, and also this condition P should be in X. And well, what we hope to find is a strengthening of P that is XP semi-generic, which means it forces that X is omega-1 contains in the generic extension of X. So this symbol means that both X is contained in XG, and they have the same countable ordinals. So, and since I will use this countable ordinals I think a lot, I will give this a name. I will call this delta X. The scale will be delta X of G. Okay, so in theory, we see the first problem that can arise if you try to do this. So you try you always try to build this Q inductively. So you first find Q0 that is semi-generic for the first forcing that you use, the Q0, and then you go on and try to find Q1 and so on and so forth. So the first step we would try to do is to find Q0, which forces this, but just for the first forcing that you use. But this is impossible if the following situation arises. If you have a subset of omega-1, which is in X, which contains the delta X, but also P0 forces, with the first forcing that you use, that S becomes non-stationary. So why is this impossible? So so this generic extension then, so let's call it XG1. So it will have some club in omega-1, which is disjoint from S. But you always have that the delta of such a structure, it must be contained in any club that is in the structure. So delta of XG must be an element of C. But we assume that delta of X is an S, yeah. But C is disjoint from S, so delta XG is in C minus S. So in fact, this guy cannot be delta X, and you've added some countable ordinals to X. Okay, so this means there's no way to find Q0. So this leads us to the following definition. So suppose I is an ideal on omega-1. Then we say that X respects I if for all S in the ideal, which are also in X, the delta X is not contained in S. So as an example, this thing that I just said is, one of the things I just said is essentially that X always respects, for example, the non-station ideal. So this is always respected. The delta X is always in any club that is in X, so it's not contained in any non-stationary set that is in X. So we can rephrase the statement here, this problem, as saying at the very least, we need that X respects this ideal right here, which contains all subsets of omega-1, which are forced by P0 to become non-stationary. And we will denote ideals of this form in this way. So we will put the forcing on top and the condition on the bottom. All right, so at the very least, we have to choose X so that it respects this ideal. All right, can we do this? Yes, we can. So this is follows from this lemma right here. So assume I is an ideal on omega-1, then in fact for any I positive set and any club in the countable subsets of H theta, you can find a Y in this club which both respects I and has delta Y in S. Maybe I should also say that Y is also an elementary substructure of H theta. How do you do this? The proof is quite simple. You take a continuous increasing sequence Y alpha of countable elementary substructures of H theta. So increasing means that Y alpha is an element of Y alpha plus 1. And a continuous means that if alpha is a limit, then Y alpha is the union of the earlier Y betas. Or this should be alpha. Okay. And we take them so that the ideal I is in all of them, and we can choose all of them to be in C because C is a club. Then remember, all ideals are normal in this talk. So by normality of I, then indeed we can find an alpha in S, so that on the one hand, alpha is the delta of Y alpha. So this thing right here will happen in the club. And also Y alpha respects I. So this is just a question of normality. I'll leave the details to you. So indeed, we may assume that we picked X in the beginning so that X respects this ideal. This is what we wanted to have. Okay. But now maybe we got lucky and we found the first Q0, which does what we want for the first step. But the same problem arises again now, right? So now we have the next force in Q1 that we have to deal with. And we want to find Q1, and Q1 should also be less than P of 1. And the exact same problem arises for the exact same reasons. Now we need that X Q1 respects this ideal here. You know, it's the same thing. So how can we arrange this? This is now more problematic. So it leads us to the next definition, so a class of forcings. So say Q is an omega-1 preserving forcing. We say that Q is respectful if whenever we are in the situation which looks like in the situation we are in right here. So think of Q in this case as the Q0. And suppose you have some countable substructure of some H lambda against some large regular cardinal. So the forcing is in Y, and Q is in the forcing and in Y. And suppose you have dot I, a name in Y for an ideal on omega-1. So here dot I, think of a name for exactly this ideal that we have to deal sort of in the second step of induction. Then one of the following holds. So the first thing is the good case that we want to be in, that there is a strengthening of Q, which forces, which is both semi-generic, so it forces that Y of G is an omega-1 end extension, an omega-1 extension of Y, but also that YG respects the evaluation of dot I. So you cannot always expect this to be true. So there are some obvious obstacles that prevent something like this from happening, which would be that Y does not respect the ideal I dot Q, which I call so this is the partial evaluation of dot I by Q. So these are all subsets of omega 1, which are already forced by Q to get into dot I. So you cannot change anything about this. This will definitely be a subset of the later evaluation of dot I in the generic extension. You cannot change it. So you want YG to be an omega 1n extension of Y. So if Y already does not respect the smaller ideal, then YG certainly cannot respect the evaluation of dot I. Okay, so respectfulness means that this is sort of the second case is the only obstruction that you have to such an R existing. And if this obstruction is not there, then you can find this very nice strengthening R that we are looking for. So respectfulness, okay. Can we have that? So assume that the strong reflection principle holds. Then in fact, all omega 1 preserving forcings are respectful. Okay, if you don't know what the strong reflection principle is, don't worry. So it will appear now in the proof at one step, and then you will see what it means. So let's prove this really quick. It's surprisingly not very difficult. So for some reason, my screen sharing froze. It's back again. Okay, so suppose Q is omega 1 preserving, and we are in this situation as in the definition of respectfulness. And we have to show one of the following things. Either we have to find a strengthening of Q, which forces what we want, or we have to show that Y does not respect the partial evaluation of dot I by Q. Okay, so take mu to be, so this should be forcing Q here to be large enough so that it's still in Y. So, and we set script S to consist of all countable elementary substructures of H mu, for which sort of the thing that we want to happen fails. So there's no strengthening of Q which forces what we want, but for Z in place of Y. So this set script S is in Y. And now we apply the strong reflection principle, and it tells us exactly that in this situation that we are in right now, we can find a continuous increasing chain of elementary substructures of H mu, such that like the relevant parameters are already in Z0. And so the strong thing about this is this third property right here. So for every alpha, either Z alpha is already in script S, or in fact, we can find no omega 1 extension of that alpha, which is in S. Okay, and by elementarity, we can assume that this sequence of sets is in Y. All right, so now we have the sequence. So now some of the Z alphas will be in script S, and some of the Z alphas will be in the second case. So we gather all the alphas for which Z alpha really gets into script S, into ZS, and we also take a generic for Q, which contains the condition Q that we are looking at. And what I claim is that in the forcing extension, the ZS gets into the ideal I. So why is this? Suppose otherwise, that S is I positive. So now these extensions by the Z alpha, they form now a continuous increasing sequence of elementary substructures of H mu of the forcing extension. And we can find a club such that alpha is the delta of Z alpha and the delta of Z alpha G, I should say for alpha and C. So these things just happen on the club, so we can find this. And now if you have an alpha in in S intersected C, so as alpha is in C, you already have that Z alpha is in, that's omega 1 extended by Z alpha G by this condition here. And this alpha is also in S. So this means that alpha is in S. The only way that this can be now is that alpha G does not respect I. So this means you can find a witness for this non-respecting. So there's some T alpha in I, which is also in Z alpha G, such that the delta of Z alpha G is in T alpha. Okay, remember this delta Z alpha G is actually just alpha. Now again, we employ normality of I, and we can find some still positive S0, which is a subset of S intersect C, and we can find one T so that on S0, the T alpha is always this one T. So you can do this because you choose these T alphas always in Z alpha G, and they form this nice continuous increasing sequence. But now we get a contradiction because by this thing here, you can easily see that S0 is a subset of T, but T is in I and S0 is supposedly I positive. So that's clearly not possible. So we have a contradiction. So the claim is true. And now there are just two cases. The first case is that delta Y is in this S. And then simply we have that S witnesses that Y does not respect this partial evaluation. So we are in the second case of the definition of respectfulness. The bad case is subtraction. And the case 2 is that the other thing happens, delta of Y is not an S. And then you find that Y intersected H mu is an omega 1 extension of Z at the index delta Y. And thus, since delta Y is not an S, and by how we chose the sequence C, we must have that this guy is not an S in script S. And if you look at the definition of script S, we find that we're in the good case. So we can find some strengthening R of Q, which forces exactly what we want. Very good. Okay, so under SAP, indeed, all omega 1 preserving forcings are respectful. So this is not always the case. Like, for example, I mean, it's clear, it's easy to see maybe that if all 4 omega 1 preserving forcings are respectful, this is quite a strong property. But in L, there are very nice forcings which are not respectful. Like just adding a subset of omega 1 by countable conditions is not respectful in L. So I don't really know what's going on with respectful forcings in just as a C context. Seems to be all over the place. I don't really know. Anyway, back to business. So we're in this case that we had this X which respects this ideal, and we take the name I dot for the next ideal that we want to respect. And let's now assume SAP. So we know that Q0 is respectful as Q0 preserved omega 1 and by the previous lemma. And we want to find this Q0, which forces that what we want. And we can do this by respectfulness, provided that X respects this ideal here. And if you look at this, it's just what P restricted to do forces to be non-stationary by a two-step iteration of the first two forcings in the iteration P. So now, how can we make sure that this helps, that X really respects this ideal? So the crucial observation here is that this is true if the next forcing Q1 only kills new stationary sets. So stationary sets that were not present in V, but only appeared after the first forcing, because then you can easily see that this ideal really is just the ideal of all sets which were killed by the first iteration is forced by P0. And then we're good because we already have that X respects this ideal. And then we land in the good case of respectfulness, and we can carry on our induction. And then this, you have to do a little bit more stuff, but this leads you to this lemma. So suppose that for all n at all stages you force a strong reflection principle, and the QNs only kill stationary sets which are new. Then indeed this iteration of length omega, it preserves omega 1. Okay, this is essentially what we've done. So if all this works out, you can just continue this induction, finding Q inductively, and you have to arrange a few more things on the side. It gives you a little more technical stuff to solve, but it all works out. Okay. So, but actually we care about F preserving forcings. So, so let's take a witness F of the Steinman principle, and we want to iterate F preserving forcings while also preserving this property of F. By the observation that we had before, it's crucial that the forcings that we use are only allowed to kill new stationary sets. This means that to stay flexible later, we want to kill as many stationary sets as possible as early as we can. So now we take a look at which stationary sets actually can be killed by F-preserving forcings. So they cannot kill the SFPs, because it follows easily from the definition of the Steinman principle here that these SFPs must all be stationary. But we've also seen this before. We can kill indeed stationary sets which do not contain some of the SFPs modulo stationary ideal and non-stationary ideal. Okay, so so since we want to kill as much as possible, we want to make sure that there are no sets of this form in the next forcing extension, sort of. So this leads us to the next definition. So we say that a forcing Q freezes a non-stationary ideal along F if for any set S subset of omega 1 and any generic of Q, either the stationarity S has been killed, so it's non-stationary extension, or in the extension it contains one of the SFPs modulo the non-stationary ideal. So this is also sort of the one-step version of trying to turn the embedding eta F into a dense embedding. Yeah, along the iteration, if you try to turn eta F into a dense embedding, for every stationary set, you have to make a choice at some point whether you kill it or whether you make sure that it contains some of the SFPs. And so this notion of forcings that I defined here are just the ones which solve these questions simultaneously for all sets which exist in V. But of course, in the extension, there may be new stationary sets. So you have to solve new questions again in the future. So this hopefully motivates Q iterations. So suppose you have a witness F of the Steinman principle, and you have a nicely supported iteration P. So what does nicely supported mean? So it's due to Miyamoto, it's some kind of countable support style support system. So if you don't know what this means, think of revised countable support iterations. And if you don't know what that means, then think of countable support, which is hopefully self-explanatory to some degree. So we say that such an iteration is a Q iteration if you only use forcings which preserve F, and then at successor stages you always force SRP, and also at successor stages the forcing you use always freezes an unstationary ideal along F. So you see that at limit steps, we've placed no requirement onto Q alpha except that it must preserve F. So essentially, Q iterations allow us to preserve to iterate F preserving forcings, but with some intermediate steps, sort of. And then the corresponding iteration theorem is that Q iterations preserve F. So it's not really an iteration theorem in the traditional sense. I do not define a class of forcings that I prove is sort of closed under iterating them. But the way you prove this is very much like proving iteration theorem. So that's why I call it iteration theorem. Okay, so this essentially works. So the main ideas that go into this, I've explained in this sort of toy example of just iteration of length omega. In long iterations, like some problems arise that you have to solve. Also we want something stronger. We just don't want to just preserve omega-1. We indeed want to preserve F. And you have to do a little more to make that happen, but it all works out. You can manage this. So in the end, Q iterations preserve F. So can we force QM now, since I sort of told you about this way of iterating essentially arbitrary F-preserving forcings? Well, not immediately. We have to make sure that these forcings that are in steps that appear here, the successor steps, that you can really find them all the time. So for this here, we have to find an F-preserving forcing which forces SRP. So of course, we know how to force SRP, but in this case, we have also this restriction of preserving F. So you have actually to find an F-preserving forcing which forces SRP. And more importantly, you have to find a forcing, assuming large cardinals, that frees the non-stationary DL along F, which turns out to be actually the more difficult part. So these are exactly dilemmas. I will tell you how to do that next week. So next week, we'll show how, assuming that there's a supercompact cardinal, you can force SRP by preserving F. And assuming there are two wooden cardinals with a measurable buff, which is kind of a funny assumption, but it works. Then there is an F-preserving forcing which freezes the non-stationary DL along F. So these two things, they will happen in the second part of my talk next week. But when you've done this thing, then indeed you can force QM. So suppose you have a witness F of this diamond principle, and you have a supercompact limit of supercompact cardinals, then you can force QM. In fact, you can turn F into a witness of QM. The way you do it is just you do Q iterations. You know that the forcings that you need at the successor steps always exist. There you make use of the supercompact cardinals that are below the top supercompact cardinal to force SRP, and you use the top supercompact cardinal to get the forcing axiom in the extensions, like always, the usual argument, like how you get PFA or MM, something like this. Okay, so I promised you this semi-proper forcing doing this. Up to now, I only talked a lot about forcings killing stationary sets, which are not semi-proper. So there's just one more trick, which the trick is just to choose this witness F of this diamond principle very carefully. So you use this lemma right here. So suppose you have omega-1 many stationary sets and diamond holds on all of them, then you can find a witness F of this diamond principle such that all these S alphas contain one of the SFPs. So what you do now, or can do now, is you can collapse 2 to the omega-1 to omega-1 by sigma closed forcing. And in this extension, diamond holds on any stationary set, and all the old stationary sets are still stationary. So by the lemma, you can find a witness F of the diamond principle such that any stationary set which was in S, which was in B, contains one of the SFPs. Because you collapse 2 to the omega-1, so now there are only omega-1 many old stationary sets. And then the observation is that all further F-preserving forcings, they must preserve the stationarity of SFP, and thus preserve the stationarity of all these stationary sets. So if you first do this and then force QM along F, then from the point of view of B, this is the stationary set preserving forcing. And since we have supercompact, we assume supercompact cardinals anyway, stationary set preserving forcing is the same as semi-proper forcing essentially. So you can find a semi-proper forcing P, which forces QM. And if you're just interested in turning the non-stationary ideal to be omega-1 dense, so this is the best assumption I have at the moment. So if you have an inaccessible cardinal kappa, which is a limit of less than kappa supercompact cardinals, then there is a stationary set preserving forcing P, which turns the non-stationary to be omega-1 dense. So if we assume these partially supercompact cardinals to be supercompact cardinals, then again you can assume P to be semi-proper. So this is what I promised in the beginning, this theorem. All right, so that's it for today. Thank you for listening. I will continue next week with these two lemmas that I skipped. Okay, thank you.
Thank you. Great talk.
Thank you.
All right, so I guess we should make time for some questions. I actually have a quick question, maybe the two lemmas that you stated and then the corollary of that, it seemed like you needed, so each of these lemmas said that there is a forcing that does something, but didn't you need a forcing that does both things at the same time to get the corollary, or?
Right, you do first, you take a forcing with the second property, and then you take a forcing with the first property. And then the two-step iteration still has the second property, but also has the first property. That's just a trick.
I see, okay.
Exactly. I mean, also in Q iterations, so there's some flexibility here. I could say that at even successor ordinals, I force SRP, and at odd successor ordinals, I take a forcing which freezes the non-stationary ideal along F. So yeah, there's no conflict, luckily.
Okay. Okay, cool. All right, yeah, thank you. Any further questions? Okay. Everybody seems happy. Okay, well, thanks again, Andreas. That was a great talk. I'm looking forward to next week.
Yeah, thank you very much. Yeah, hope to see you all back next week. All right.